Here we go. This is Mr. Bishop back with you. We are on day 3 of chapter 3 here in our finite math notes. The topic is still linear programming problems. So this is just more like day 2 continued. So I want to start by just recalling a couple ideas from the last video. So I'm going to bring a couple of those things back. So when we're doing linear programming problems, we're talking about real-world problems that have an objective function that we're going to either maximize or minimize. Right? So a lot of times it's like maximum profit or minimum cost. And the other thing that we talked about with real-world scenarios, we know they have a finite amount of resources. So that could mean their employees, their labor, materials, the time that they have in the day, their capital, right, their money, the space in their building, their equipment, all sorts of things, all sorts of resources they have that could be finite. And what we're going to do to help that business or that situation optimize their objective, we're going to model these resources, right, these finite resources, using linear inequalities. We call these the constraints. All right, so we also discussed that in the last video too. So let's take a look at the first problem here from the day 3 worksheet. I'm going to go through this one with you, and then I'll leave the other 2 problems for you to do. So it says Mr. Holloway decides to feed his pet Siberian Husky 2 dog foods combined to create a nutritious, low-sodium diet. Each can of brand A contains 3 units of protein, 1 unit of calories, and 5 units of sodium. Each can of brand B contains 1 unit of protein, 1 unit of calories, and 4 units of sodium. Mr. Holloway feels that each day his dog should have at least 12 units of protein and 8 units of calories. Okay, so let's start by taking the numerical values from that problem, from that scenario, and completing this chart. So the protein for brand A, it looks like that has 3 units of protein and 1 unit of calories. So I'm going to put a 3 there and then a 1 for the calories, and 5 units of sodium. So 5 right there. And then for brand B, we've got 1 unit of protein, 1 unit of calories, and 4 units of sodium. There we go. And then the dog said, like, for the dog to be healthy, the dog should get at least 12 units of protein. So I'm going to put 12 for the protein requirements and 8 units of calories. There we go. All right, so far so good. We've got the table completed. We're going to use those numbers to help us for part B, which says, let X be the number of cans of brand A. Okay, so put X's for brand A. And Y is going to be the number of cans of brand B. So this is going to be Y's this way. Referring to the chart, give the 2 inequalities that X and Y must satisfy to meet the requirements for protein and calories. So in other words, we need to come up with our constraints based on the protein and the calories that the dog needs. So let's start with protein. Let's start with the protein one. We know it's 3x plus 1y, and then we've got a 12. The question is, what symbol, right? It's an inequality, so is it less than or equal to or greater than or equal to before the 12? And I see kids mess this up frequently. It says the dog should have at least, right? The dog should have at least 12 units of protein and 8 units of calories, right? So we're talking about protein. If it says at least 12, then that means between brand A and brand B dog food, you better have greater than or equal to 12 units of protein. So 12 is the minimum, right? We want to have at least 12 units of protein. We don't want to starve the dog or feed it less than 12, right? A apparently that wouldn't be good. That would be below the suggested amount. So it needs to be greater than or equal to in this case. Let's go to the calories. So similar fashion here. For the calories, we've got 1x plus 1y. And again, it needs to be greater than or equal to that minimum number of calories, which is 8. Or I guess it's not number of calories, it just says 8 units of calories, whatever units they're measured in. So that's perhaps the biggest difference between day 2 and day 3. It's still a real-life scenario that we're still setting up the constraints for. You'll notice, though, on day 2, these all tended to be less than or equal to, and now they're all greater than or equal to a certain value. All right, so part C, I think you know what we're headed for there. It says, give the inequalities that x and y must satisfy because x and y cannot be negative. So we know that x has to be greater than or equal to 0 and y has to be greater than or equal to 0. In other words, you can't have negative dog food. You've got to have at least 0 or more cans of each brand of dog food. All right, so those are good. Those are always going to be there when we're talking about a real-world scenario. And then the last part here for part D, it says express the amount of sodium, which in this case, this is our objective function. The dog's on a low-sodium diet, in X cans of brand A and Y cans of brand B. And we can just look at the last row of our table here for sodium, right? So I'm just going to, how about I use the letter S here? I think day 2 we used P for profit. I'm going to do letter S for sodium. We get 5 units of sodium from brand A and 4 units of sodium from brand B, and that would be our objective function in this case. And since the dog's on a low sodium diet, we'd like to get that sodium count to be as small as possible. All right, so again, the biggest difference between day 2 and day 3, day 2, you're going to tend to have these greater than or equal to signs, just given the scenario that it's based on. We're still talking about real-world problems that have a finite amount of resources. We're still setting up our linear programming problems. Okay, that is all for day 3. Thanks for watching.